Hey pals, welcome to another video of quantum field theory. In today's video, we'll be deriving a more practical version of the Klein-Gordon equation solution. So I've already made a video for the solution to the Klein-Gordon equation, and that's like my second video of this quantum field theory series. So I recommend checking that one out before watching this one, since I'm going to sort of assume a bit of knowledge from that video. So with that being said, let's do a brief overview of what we did in that video. And ignore this for now, this will make sense later. So here's the solution to the Klein-Gordon equation that we derived in that second video, and we can see that it's a superposition of plane waves. So here's the notation for x mu and k mu. I don't like this notation, but most people use it. In my second video, I used a slightly different notation, which I think it's better, but most people like using this notation over here, so we'll use it for this video. So, yeah, and for a real scalar field, the B coefficient is equal to the complex conjugate of the A coefficient, and both are functions of the momenta, including the energy. And this 2 pi to the 4th over here is just some factor for the Fourier transform that we don't have to worry too much about in this video. So here's a quick derivation. Here's the Klein-Gordon equation. To solve it, all we had to do is use an ansatz of e to the ik mu x mu and e to the minus ik mu x mu. These are our plane waves. And then we got this equation over here, and this is solved for the case where our particle is on shell. Alright? So next we can just sum both of these solutions together, weighted by these constants. And we can do this since the Klein-Gordon equation is a linear differential equation. So you can just check this yourself. This will also be a solution. And then we can just sum over the momenta k mu, and that turns the sum into an integral since the momenta is continuous, and we arrive at this equation over here. And that's what we arrived at the last video, in the second video of this whole series. And something that I should mention is that there's a small problem with the solution. This solution is correct, right? This is the solution to the Klein-Gordon equation, but it doesn't actually encode the fact that k mu equals m squared. Like, we have to say, if k mu equals m squared, then this equation is a solution. But how can we write this equation in such a way where we don't have to make that statement? Well, we can do this by using the delta function and the Heaviside function. And that's the topic for today. We want to derive a more practical version, a more obvious version of the Klein-Gordon equation solution. So let's do that right now. So first of all, we're going to define this part of the Klein-Gordon equation solution as ... And we're going to do that because it's pretty long to write, so we're just going to just shrink it down to just ... Alright, so what we can do is we can say that the solution to the Klein-Gordon equation is the integral over the 4 momenta, and then say that it's the delta function of k mu minus m squared times what's called the Heaviside function, which is a function of k naught, the energy, and then times ... So we have to talk about what this and this mean. Okay, so first of all, let's deal with the delta function. We know that the delta function is just a function of some variable, let's call it x, and it's defined as being infinity if x equals 0, and then 0 if x is not equal to 0. So if you were to graph out the delta function, here's like say x and here's like y, the delta function peaks at x equals 0 and everywhere else it's 0. So this delta function is very useful in physics since it can like sort of pick out the location of a particle. And we can encode this by integrating the delta function and multiplying it by some function, say f of x. So we can have say like f of x and then delta of x minus a. So delta of x minus a is going to be a function that peaks at x equals a. So if here's a, then we now have this for our delta function. So it can encode the location of a particle. This integral, when we integrate over x, is going to be equal to f of a. That's a cool property of the delta function. So again, it can sort of pick out where the particle is, and we use delta functions a lot for that. So that's just a brief rundown of delta functions. I recommend looking more into what a delta function is, because we're going to use it a lot in our quantum field theory series. So the next contender is also called the Heaviside function. So the Heaviside function, it's a function of some variable, let's call it x. It's going to be defined as being 1 if x is greater than or equal to 0, and then 0 if x is less than 0. So if you were to plot this Heaviside function, we get this. So here's 0, and then here's 1. It's going to be 1 if x is positive, basically, and 0 if x is negative. So it sort of picks out the positive numbers from the negative numbers. It projects all the positive numbers on the x-axis onto 1 in the y-axis, and then it projects all the negative numbers on the x-axis to 0. So that's the Heaviside function. And a cool property, which is not that much relevant for our video, but still a cool property, is that the delta function can be said to be the derivative of the Heaviside function. And we can see this because, if you think about it this way, what's the derivative of the Heaviside function? d over dx. Well, if x is greater than 0, so if x is positive, or greater than or equal to 0, if it's positive, then it's equal to, then the function is equal to 1, right? And the derivative of 1 is going to be equal to 0, right? So it's 0. And if x is less than 0, actually I should say just strictly greater than 0. For now, let's not include the equal to 0 part. So if x is less than 0, well then it's also 0. The derivative is also 0 since it's just a line, it's a constant slope. Okay? But what if x is equal to 0? What's that? Well, we have a discontinuity at x equals 0. Our function just breaks apart here. And we can kind of connect this with a green line. And the slope here is just rise over run. The rise is just 1, and the run is 0. So the slope will be infinite at x equals 0. So we get infinite. And what's a delta function? Well, the delta function is just a function that's infinite at 0 and 0 everywhere else. So the delta function satisfies the properties of the derivative of the Heaviside function. So we say that the derivative of the Heaviside function is the delta function. That's just a brief aside, which I think is like pretty cool. We're not going to use that for this video, but it just builds some intuition with the delta function and the Heaviside function. So with those definitions, we can understand why we insert those things in our equation. So this is still a solution to the Klein coordinate equation, all right? It's still a solution because like if you were to plug this into the equation, we get 0. So here, this delta function encodes that k mu equals m squared. So it encodes our mass on shell condition, because remember that if our delta function is like if the input here is non-zero, then we get 0. So this tells us that if k mu does not equal m squared, it tells us that our field is 0. So, and that's still a solution to the Klein-Gordon equation, right? But just for a particle that doesn't really exist, right? So that's how we encode that condition with that delta function. And the Heaviside function, it encodes the property that particles have positive energies. So we want to only look at particles that have positive energies, and we do so for many reasons. First of all, we haven't really observed a particle like without any forces acting on it with a negative energy. We only observe positive energies. And if we do allow negative energies, there's a whole problem where you have a particle falling down in energy levels. If you want to learn more about that, look up the Dirac C. I also talk about that in my, I believe, 3rd or 4th video on the Dirac equation. But we only want to look at particles that have a positive energy. So that's why we put in the Heaviside function as a function of k naught. K naught is also the energy of our system, by the way. So remember that this is just 1 if x is positive, basically. If x is positive, and 0 if x is negative, blah, blah, blah. So this just tells us that if a particle has a negative energy, the field is 0, so the particle does not exist. And if it does have a positive energy, our function is just 1. So that's why we use the Heaviside function there. Sorry for the noise, siblings, so not much you can do about that. So yeah, we have this equation over here, and that's the motivation for doing this. Now the question becomes, how can we solve this integral? How can we simplify this equation a tad bit? So to do that, we have to use some sneaky property of the delta function over here. So let's copy that, paste that. I have to use this property. So first of all, let's expand. Let's actually just look at what term should we look at? Let's just look at this term over here. We're going to solely look at the delta function. So we can expand k mu as just k naught minus the sum of ki minus m squared, right? And to make things a bit more familiar to us, let's replace k naught with E for the energy. Let's replace the sum over the 3 momentum components squared as just p squared. So some people might say, I don't like how you're doing that, like it's kind of a basic notation for the p especially, but like it's intuitive and you get the point. So let's use those substitutions. So we now have delta of E squared minus P squared minus M squared. And you can see why I did this, because the famous equation is E squared equals P squared plus M squared. So that's why I used those symbols, because they're much more familiar to us. So we now get that, right? And we can also rewrite this as delta of E squared minus P squared plus M squared, right? So that's our delta function now. And what we can do now is we can notice that this is a difference of squares, kind of. So to see that, let's define this quantity as my pen just died. 1 second. 1, 2, 3, 4. Okay, so let's define this quantity as omega k squared. So omega is being defined as the square root of p squared plus m squared. So we now have that our delta distribution is e squared minus omega k squared. Alright, so this is of course the difference of squares. So you can just rewrite this as being e minus omega k times e plus omega k. That's just the, what is it called, binomial expansion or something of the difference of squares. So I now have this equation over here, and now we can use this guy. Now we can start using him over here. Let's copy that, let's paste that. So this just tells us that the delta function of f of x is this guy over here. So this is a sum, right? So this is going to be equal to delta x minus a, where a is just some constant, absolute value of the derivative of x with respect to x, sorry, derivative of f with respect to x, then plus, so here's a1, make it a bit more clear, here's a1, then plus delta of x minus a2 over df over dx. So that's the expansion of a delta function where we have a function that's living inside the delta function. Weird verb to use, but it kind of works, right? So yeah, we have that. So we can define f of x here. So let's just take this guy over here. Let's isolate it. We can say that this whole thing is defined as f of x. Or in this case, it's going to be really f of e, since e is our function, and we're of course integrating over e as well, since if we were to expand this, it's just dk3 and de. So we're e is our x in this case, basically. So delta of f of e, following this rule, is going to be the sum of delta e minus a1, sorry, ai, over the derivative of f with respect to e. Let's first evaluate what this derivative is. So df over de is going to be d over de of f. F is just this over here, which is just equal to, remember that it's just e squared minus omega. My pen died again. I don't like how Apple pens have like a very small battery life. So you just have to wait awkwardly for like 5 seconds. Okay, let's see if it's working now. So minus omega, yep, omega k squared. Oh, let's write a better omega. Minus omega k squared. Alright, so this derivative is going to be equal to 2e. Even though e equals omega k, we're going to treat them as independent variables, alright? Because we haven't really established that they're equal to each other just yet. So this is going to be equal to 2e. So df over de is 2e, so delta f of e is going to be equal to the sum of delta e minus ai over 2e. We can factor out the 2e out in the end, and now we just have to expand our summy thingy. So that's just delta of e minus a1, yeah, plus delta of e minus a2. So let's move this down a bit. Thought there'd be a fraction or denominator. Okay, so now we have this, and we can kind of see what a1 and a2 are. So again, here was our formula for like f of e in our delta function, right? So oops, let's bring that back. So we can see that e1 is just going to be omega k, and then a2 is like minus omega k. So A2 is minus omega k. So this basically comes down to being 1 over 2e of delta of e minus omega k plus delta of e plus omega k. So now we get that. And again, this was our formula for delta of k mu minus m squared. So we can go back to our original equation, and all we have to do now is plug in what we found for this. Let's first look at what the Heaviside function does to this delta function. So we have to apply the Heaviside function in the end. Doing that, we get, so basically we're saying that delta of k mu minus m squared times the Heaviside function of k naught, that's going to be equal to 1 over 2e times delta e minus omega k plus delta of e plus omega k. And then in the end, we just do Heaviside function of e, since k naught equals e. So now we have that. Now here's the cool, really nice part. Remember that omega k is just a square root of p squared plus m squared. So square roots have positive and negative solutions, right? So if we took omega k to be, if we took it to be negative, right? That means that this would be positive and this would be negative. Here, let's write it. Let's look at it like this. So for this to yield a non-zero contribution, here E has to be equal to omega k, and here E has to equal minus omega k. And since omega k equals plus or minus p squared plus m squared, if we took omega k to be positive, for example, then this is positive and this is negative, right? If we took it to be negative, though, this is negative and this is positive. Let's choose for it to be positive because it's more simple conceptually. So let's choose omega k to be positive. So when our Heaviside function acts on this integral, it's going to kill this term. Well, that's a strong word. It's going to delete that term, right? Because this term describes e being negative, right? But our Heaviside function is only non-zero if e is positive. So, but here e is negative. So when our function goes onto this guy, we get 0. When it goes onto this guy, we get 1. Or sorry, not 1. We get the same thing since this function is 1. So basically, this is going to be equal to 1 over 2e times the delta function of e minus omega k times 1, or just the same thing. So now we can look back at our big old integral over here with the big nasty functions. We can just copy that. We can paste that. We're almost done, guys. Hang in there. We now know that this is just equal. All of this in the yellow is just equal to 1 over 2e delta e minus omega k. So our formula for our field, phi of x mu, is just now the integral over, we're going to separate this measure into p and dE. So over 2 pi that times 1 over 2e, so we have the 2e over here, times delta of e minus omega k dot. So now we can use the cool property of the delta function, where basically f of x delta of x minus a equals f of a. Very convenient property of our delta function. So that just gives us this. We just now have a function. Oh, this should be a to the fourth, by the way. So now we just have our integral over dE is now gone. So now I have of that over that over that, and our delta function is gone now. So now what we can do is we can multiply by a factor of 2 pi. Now this part may seem pretty arbitrary, but we're able to do that by just factoring out a factor of 2 pi in front of our Fourier momentum coefficient thingies. So we just do that so that we can just cancel out this 4 to get a 3. Since if this is 3 and this is 3, it makes the Fourier transform make a bit more sense. It's just kind of the convention. So now we have this over this 2e. Oh, also, e equals omega k, right, for our delta function. So we should really write 2 omega k instead of 2e. But since they're equal, it's still okay to do that. So now we have this. And by actually plugging in our thing, and by substituting p back for k, we get integral over our momenta over 2 pi cubed 2 omega k times a of k mu e to the minus I k mu x mu plus b of k mu e to the I k mu x mu. And this is a much more simpler equation compared to the thing we had to start with. So yeah, this looks pretty nice so far. Pretty nice. And what we do now is we don't like how our coefficients are a function of k mu for whatever reason. So we want to separate 2 omega k into the square root of 2 omega k times itself. Pretty cool. So now we get integral over the 3 thing. I'm getting pretty tired right now, if you guys couldn't tell already, which is why I'm kind of like not using the exact language of the terms. But we can distribute one of these guys into our thing, and we get a of k mu over square root of 2 omega k e to the minus I k mu x mu plus b of k mu blah blah blah. It was my birthday yesterday, by the way. I wanted to make a birthday video, like a birthday paradox video, because it's birthday thing, but I didn't get around to doing it. But I'm 17 now, by the way, so yeah. But like, if you include the fact that leap years exist, and there has been 6 leap years since my birthday, in August 2nd, 2005, my birthday technically was 6 days before my official birthday. So technically speaking, leap years kind of set that back for everyone's birthday, which is a cool thing to think about. So I'm 17 now, by the way. So yay, hip 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 hooray for me. So yeah, now we have this thing over here. Oh, the pen just died. Well, let's charge it again. 1, 2, 3, 4, 5, 6. That's charged. Okay, so what do we do now? Now we can redefine a... What? The pen is still dead. Okay, let's charge it again. Just awkwardly wait. That's enough time. Okay, if it's still not working, then something's wrong with the pen. Okay, good. So now we have we can redefine a of k, where k is the 3 momenta. You can define that as being a of k mu over the square root of 2 omega k. Same thing for this b guy over here, b of k mu. We read it, so we can kind of do this since like we're dividing by omega k to square root of 2 over omega k. So it's kind of going to like remove one of the. I'm trying to think of like how to say this precisely. It's going to kind of like remove like the e thing. Just take this as a definition, but by doing that we get that. So our thing is only a function of k instead of k mu, and that gives us our final desired form of the Klein-Gordon equation as being the integral over this, 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 and over this. And now this video is over. This.